Alien Earth collaboration, and he does work on exoplanet demographics and also survey simulation for the ELTs. So with that, I'll let Kevin get started.
Thanks, Noah, and thank you everybody for coming and letting me give this talk here. As Noah said, I'm at the U of A as part of the NASA-funded Alien Earth project. We do all sorts of different projects related to exoplanets, their formation, their habitability, observability. It's a very large project. And so I'm going to talk to you about one aspect of our research, which is providing simulations for future telescopes. And this is using the Bioverse software, which was originally developed by graduate student Alex Bixel for simulating surveys for upcoming large space telescopes. And so I encourage you to go check out Alex's original paper. And we're now working with Noah to try to do some more work on Habitable Worlds Observatory with Bioverse simulation. But what I'm here to talk to you today about mostly is the prospects for observing biosignatures with extremely large telescopes, the upcoming 30-meter class ground-based telescopes. And I have a couple papers out here on the subject. Just either go search for my name. You can use this QR code. I highly encourage you to go check out these papers. But I will be talking to you about some of my recent work. So why am I doing this kind of work? We are very motivated by some of the highest priorities of the decadal surveys. So in Astro 2020 and the Planetary Science and Astrobiology decadal surveys, fully 1/3 of their highest priority areas are about the search and study of exoplanets and their properties, specifically focusing on potentially habitable worlds. And so we are very much guided by the search for life out there, us who work in exoplanet land. So we're glad that the decadal surveys acknowledge that the search for life is really crucial to understanding our place in the universe. When we are talking about biosignatures, there are some trade-offs between using ground-based telescopes and space-based telescopes. I'm not here to tell you which one is better because I think both are needed and both potentially fill different areas of space that we need to explore. Ground-based telescopes have the benefit that you can build much larger aperture telescopes, at least currently. You can do continuous instrument development and maintain those instruments for a long period of time. These telescopes typically have a longer support lifetime. We're talking about half a century support lifetime, potentially longer, whereas space telescopes, usually they're launched and have maybe, if you're lucky, a 5-year lifetime, and only if it's Hubble, you're serviced and have a 30-year lifetime. So ground-based telescopes, you can, as long as you have the funding and people to maintain the telescope, these telescopes, some can last for potentially hundreds of years. Ground-based telescopes are also generally less expensive. When we are talking about the extremely large telescopes, we're talking about a 30-meter aperture for about $2 billion, whereas something like JWST or Habitable Worlds, we're talking about an order of $10 billion. So we can get a much larger aperture at a much lower cost, but when we're looking through a telescope from the ground, we have to deal with our pesky little atmosphere. And if we're trying to detect atmospheres on other worlds, our atmosphere can pose a problem, especially if we're looking for signatures of life. In space, you can also have, you're more able to do continuous observations. You can stare for a longer time. There are fewer pointing limitations. You're not necessarily limited by hemisphere. As long as you're not pointed toward the sun, you're generally okay. And then there's also no need for high-resolution spectra. One of the ways to get around our pesky atmosphere is to go to really high resolution, and I will talk a little bit more about that in this talk. In the background here are just the relative sizes of the European ELT, the TMT, and the GMT, the 30-meter telescope, and the Giant Magellan Telescope. And then over here is JWST, its aperture. Also, this is just sort of a rough timeline of the current state-of-the-art facilities for exoplanet atmosphere characterization. We have Hubble and James Webb up there currently doing wonderful things, breaking new ground every single day. I see a cool new paper. On the horizon, we have a few missions looking at either finding more planets or going into their atmospheres more. So we have Pandora, Plato, Roman, and Ariel coming up soon. And then in the early 2030s, we anticipate the first giant ground-based telescopes coming online. So currently, the ELT, the Extremely Large Telescope, is going to be first online, possibly shortly thereafter, followed by the GMT and TMT. But the current U.S. ELT program funding situation is up in the air. But the ELT and TMT have broken ground, and they are currently building those facilities. And then way off in the future, but we're hoping about 20 years from now, Habitable Worlds will launch. And we have a lot of great people, and some who couldn't be here today because of development of that telescope. But Habitable Worlds is about 20 years in the future. So the ELTs are coming online soon. This talk is broken down into two different areas, including transmission spectroscopy and what we can do with that, and reflected light spectroscopy. For transmission spectroscopy, we require the planet transit in front of its host star, and we can peer into its atmosphere, whereas for reflected light spectroscopy, we have to remove the signal of the host star, and then we can directly image and get a spectrum of the planet. So we first have to get rid of the stellar signal. Here is a sort of cartoony picture of an Earth-like exoplanet's transmission spectrum from optical to mid-infrared wavelengths. This shows a handful of molecules that are present in our atmosphere that that we can use as to search for life, including oxygen, ozone, methane, carbon dioxide, and water. I won't necessarily say water is a biosignature, but we think water is necessary to have life. So finding water on a planet will be crucial to saying whether or not the planet is potentially habitable for Earth-like life. This picture I've seen in a lot of places. It's from the, I think, Louvois report originally, and then I think it was in the Decadal survey. But this is showing that Earth's atmosphere has evolved over time. Early atmosphere had almost no trace of oxygen. About 2.5 billion years ago, these little critters, cyanobacteria, were the first to produce large amounts of oxygen in our atmosphere. And then again, another about 500 million years ago, there was another just significant increase in the amount of oxygen in Earth's atmosphere. And so when I'm giving this talk, I'm going to focus mostly on modern Earth atmosphere, but for a majority of Earth's history, Earth has not had present-day levels of oxygen. So when we're searching for planets, any detections are going to come from those with a lot of oxygen. As I will show you, it's going to be actually tough to even observe present-day Earth-like levels of oxygen. But if we had Proterozoic Earth or Archean Earth, it would be a lot harder to. So with that caveat, we have a handful of other caveats. I will be focusing on oxygen. Over here on the left, we have, in our own atmosphere, we have oxygen, ozone, water, methane, and CO2, but we don't have significant quantities of carbon monoxide. And so that's what our Earth's atmosphere looks like. But we could potentially detect oxygen in many different atmospheric scenarios, but we couldn't necessarily say, oh, these planets actually have life, because at least Earth-like life as we know it, because there are many other scenarios that you could potentially create oxygen in an atmosphere, but if you don't have, say, water or methane in certain abundances, or if you actually find CO, then it's unlikely that oxygen was dominantly created through biological processes. So you have to be careful in your observations, and you have to observe more than just oxygen. And I'll talk a little bit about that later. But on Earth, oxygen is created primarily through biological processes, most commonly through oxygenic photosynthesis, where we have plant life, which takes in a little bit of energy from the sun and converts carbon dioxide to oxygen. You can't see the reaction down here for those in the room, but yeah, we create oxygen through plants, through this nice process of photosynthesis. We've observed oxygen in our own atmosphere back in the early 90s when the Galileo space probe was on its way to Jupiter. It took a look back at Earth and got this nice, pretty spectrum. I know it doesn't look like much, but there's a whopping O2 bands there, and they saw oxygen and methane in extreme thermodynamic disequilibrium. And the best way to interpret that is that this is from some sort of biological process. So we're using that sort of information to infer that exoplanets must be similar, at least if life developed in similar ways. But our friendly neighborhood space telescope is unlikely to detect oxygen on Earth-like exoplanets. It just it doesn't have the collecting area. It's not sensitive enough to detect oxygen on Earth-like planets. It will also be fairly hard to actually detect any biosignatures with JWST on Earth-like planets, again, with that caveat. These are just some plots showing some models of different biosignatures and the distance to the star and the number of transits required to actually observe that biosignature. So, for example, if you take a look on the right at an Earth around a TRAPPIST-1-like system, at the distance of TRAPPIST-1 is about 12 parsecs, you might be able to observe, I think, methane and CO2 on the order of like 5 or so transits, hopefully in pretty good conditions. But as we're learning with new JWST data, and especially with M-dwarfs, interpreting a signal from an atmosphere and disentangling that from the star is really challenging and proving to be challenging. So even the most accessible biosignatures are proving to be kind of hard. Hopefully some of these M-dwarf planets have atmospheres, and that's what we really need to know. Do these planets have atmospheres? And then we can go the step further and look at biosignatures. We also have to be very careful in our interpretation, and especially our interactions with the news media, in claiming something is a biosignature. Many of you might have seen this plot, this really pretty spectrum from K2-18b that has a signal of methane and carbon dioxide in the atmosphere. And great, we have a couple of biosignatures, but K2-18b is not necessarily Earth-like. It's, I think, about 2 times the radius of Earth. It's more likely to be one of these hydrogen, water, ocean, Haitian planets. And so is that truly Earth-like? I don't necessarily think so, but there could be some weird extremophiles that live here. But I think it's more likely that these molecules were created by some other process that's non-biological. But more data will hopefully always help us. I think the wildest claim here was this dimethyl sulfide claim at like 1 sigma, and people went crazy about that. But we'll see what happens to K2-18b in the future. But moving on to extremely large telescopes, there have been a handful of studies that say that these extremely large telescopes will be able to probe Earth-like levels of oxygen via transmission spectroscopy. But these previous studies did not fully consider a realistic stellar sample. They just used sort of model values of different star types. But we have this wonderful new data set of Gaia that basically gives us precise stellar properties. And I went ahead and generated a uniform stellar catalog with that. These studies also didn't fold into account planet occurrence rates. With the Kepler mission, we have better constraints on how common certain types of planets are. Very importantly, these studies did not account for relative system velocities. As I was saying earlier, we are trying to look for these biosignatures in atmospheres of other planets while looking through our own atmosphere. And so you have to disentangle our signature from Earth from the signature of another planet. And you have to account for the motion of the other planet around its star as in addition to our motion around the sun to be able to disentangle those lines. And then these studies did not consider fully target observability. We are observing from the ground. There are only certain times of year that we can observe targets. Then if we're looking at transiting planets, that also further constrains when we can observe planets. So here comes Bioverse. This is a statistical survey and testing framework. It's open source, available on GitHub. It is intentionally very modular. And so there are 3 overarching modules where we can generate a sample of stars and planets. We can then simulate a survey from either ground-based telescopes or space-based telescopes. And then we can, in the 3rd module, use this to test hypotheses. In the first one, if we inject some sort of trend, we can then formulate some hypothesis and test what kind of survey parameters are needed to be able to fully test this hypothesis. And then we can calculate and determine the statistical power. And so using this modular framework, we can account for what previous studies did not. So this starts with the generation of a uniform stellar catalog using the most recent Gaia data for targets within about 100 parsecs. I generated a uniform stellar catalog of parameters, including temperatures, radii, and masses. I compared those values in these plots to known exoplanet host systems, and for temperatures, we were within about 1% on average of the literature values, for radii within about 3%, and masses within about 5%. So we know that our catalog is very good, but it's on a very uniform basis, which is necessary for large survey studies and in the future demographics studies. Just one side note is that when you compile this catalog, you can learn something about your stellar population. And these are histograms at 5, 10, 15, and 20 parsecs of the local stellar neighborhood. And what kind of stars are most common? Well, M dwarfs overwhelmingly are most common, and they peak around M4, are our most common neighbors. So those might be our best bets to look for planets or look for planets with life. Another side note about M dwarfs, especially when you're looking at transiting planets, mid to late M dwarfs are the most favorable for habitable zone follow-up because the habitable zones are closer to their star, which means the planets orbit more frequently, there's a higher geometric transit probability, and it'll take potentially less time to actually build up some sort of signal of what you're trying to detect. However, when you take a look at planet occurrence rates, and specifically eta Earth, or the frequency of Earth-like planets in the habitable zone of their host star, we have some constraints from Kepler, but there weren't very many planets found in the habitable zones from Kepler. So a lot of the eta Earth values are extrapolations from models. And so the A to Earth values range from probably about 5% at the lower end to maybe about 60 or 70% on the higher end. And so when you consider different literature values of A to Earth and then throw it into some basic simulations, other than the sort of higher end of A to Earth values, we don't necessarily expect a transiting habitable zone Earth within about 10 parsecs. We do have the TRAPPIST-1 system at about 12 parsecs, so we know that there are some nearby transiting systems, but we're going with the assumption that there are potentially some more transiting systems that we just haven't found. Yeah, this is around all stellar types, but M dwarfs overwhelmingly dominate the. However, if you look at the dashed lines up above, non-transiting systems are about 2 orders of magnitude higher in numbers than the transiting system. And I'll get to that a little bit later. Again, for transmission spectroscopy from the ground, we have to go to really high resolution. These are example R equals 100,000 spectra of the O2 A band on the left, and then the O2 near infrared band on the right. So the top is an exo-Earth transmission spectrum. The middle panel is what our Earth's atmosphere is going to look like, and then the bottom panel is what the star looks like. We're assuming that we can effectively remove the signal from the star at these wavelengths, and then we just have to disentangle the exoplanet signal from our own. And so for that, we have to basically avoid different relative system velocity space. So this video, there's an exoplanet transmission spectrum on the top, Earth signal in the middle, and then sort of just the combined signal on the bottom. And so as I move through this animation, when it turns orange on the bottom, those are relative system velocities that we can't disentangle our signal from the exoplanet signal. And so in our observing simulations, we just have to make sure that we avoid when planets are transiting at that specific relative velocity. So we have all that information. Now we need sort of a instrument performance model. And so this plot shows the number of transits it will take to probe Earth-like levels of oxygen with the ELTs. This is assuming the GCLEF instrument on the GMT. It's a R of 100,000 instrument. We're only assuming white noise, and we're, again, assuming a 3 sigma detection. And so, for example, if your telescope is the diameter of the GMT, for a planet orbiting an M4 star at 5 parsecs, it'll take something like 25 transits to get a 3 sigma detection of oxygen, if this planet even has any at Earth levels. If you go to 10 parsecs, we're now talking about like 100 transits. When you go to bigger aperture, of course, you need fewer transits. You can build up the signal quicker. If you had a hypothetical 100-meter telescope, which would be fabulous, you could do these things relatively quickly. But we have our instrument model, and now we have all of the components to run a Bioverse simulation. So we used some recent literature estimates of A to Earth for specifically M dwarfs, because again, those overwhelmingly dominate our planets or our nearby stars. So we used an A to Earth estimate of around 15%, which is A to Earth from M dwarf calculations. We determined which Earths are transiting and if O2 is observable at the simulated times of transit based on our simulated population of Earth. Then we calculated how many years it would take to probe Earth-like levels of oxygen. Lather, rinse, repeat in a Monte Carlo fashion. And then we sorted all of those simulations by the number of years it would take to probe oxygen. And then we took the sort of median of the first through nth planets. And from those simulations, this is what we get. Here I'm showing individual telescopes, so the GMT, TMT, and ELT, and the number of planets that we can survey for Earth-like concentrations of oxygen. And even if we combine the signals from all three ELTs, we expect it will take about a century to observe oxygen on a single planet. If we had a larger aperture telescope, that would be significantly quicker. But this is assuming that we require a full transit for detection. You could imagine slightly more optimistic scenarios. Maybe you don't need a full transit. Maybe you only require a partial transit, and you can somehow, through the cross-correlation function, see some movement and see that there is something there. And so if we go with a partial transit scenario, we can reduce the observing time by a factor of 2. It'll still take about half a century to observe oxygen on a single planet, but that's slightly more optimistic than a century. And if our goal is to detect life out there, then maybe we allocate the resources. Well, let's think about an even more optimistic scenario. What about a higher resolution instrument? If we go from R of 100,000 to R of 500,000, the oxygen lines get narrower and deeper. And so there's less effect of blending at high resolution. So you can potentially observe at more times. So our most optimistic scenario, that again reduces our factor of 2. If we require only partial transits, go to super high resolution. Now we're talking about 25 to 30 years for a single oxygen. You can maybe convince people that that's worthwhile, but it would be kind of a hard sell. But those were simulated planets. What about real systems? We already know about TRAPPIST-1, and depending on who you talk to, has between 2 and 4-ish planets in the habitable zone. Here's a simulation for the full transit mode. Let's go with TRAPPIST-1E, which I guess a lot of people think is our best bet for finding biosignatures. It'll take maybe 30 to 40 years to get the signal of oxygen. Again, let's go to our more optimistic scenarios. Now we're talking 20 years, or if we have a high resolution instrument, now we're talking about 12 years. That might be, you might be able to convince somebody to give you all of the observing time to observe TRAPPIST-1E at every single opportunity with all the ELTs for a decade. And if it's just a transit, it maybe takes an hour, or if this is a partial transit, you can observe for like less than an hour. Maybe you can convince them to give you all of the time to observe this. But let's talk about, there's more to life than just oxygen. You're going to have to detect potentially more biosignatures, or you're going to want to detect oxygen on multiple planets. If you observe oxygen on multiple planets, then it is fairly likely that oxygen was created through biological processes on some of these planets. But this is work by Miles Curry, who I think is coming here like in a week to be a postdoc here. So I'm sure you'll hear more from Miles about this work. But this is Miles's work on transmission spectroscopy of all biosignatures. Again, this is the sort of simple model which tells you the number of transits that you need for a 3 sigma detection. But it shows oxygen over here on the left. These are just different atmospheric scenarios, but you sort of get the idea of where all of these points are clustered. Methane and CO2 seem to be a lot easier to detect than oxygen or carbon monoxide or even water. So we're going to hopefully run soon some Bioverse simulations to look at how long it will truly take to observe methane and CO2. But moving on from transmission spectroscopy to reflected light spectroscopy, as I was showing this plot earlier, we have 2 orders of magnitude more non-transiting planets than we do have transiting planets. So what can we do with those systems? Well, we can go look at them in reflected light. And when we're talking about reflected light, it's all about contrast. For Habitable Worlds Observatory, we're going to be in space, so you can, assuming their coronagraph systems can work to extremely high precision, they're mostly going to be looking at sun-like stars and achieving contrast up to 10 to the minus 10. M dwarfs are, again, a bit more favorable from the ground. You don't have to reach nearly as high contrast. You can get away with 10 to the minus 8, and that's sort of the goal of these instruments in chronograph systems, to reach something like 10 to the minus 8 in contrast. There are some missions that are going to be looking at basically thermal infrared, mid-infrared wavelengths. The contrast is even better at those wavelengths, but if you want more information, talk to Avi about that. So here I'll walk you through this plot. We have wavelength versus separation at 2 lambda over d, which is sort of the minimal inner working angle that we think we can potentially see a signal of a planet for some of these direct imaging systems. And so the sort of diagonal lines are each of the telescopes at different wavelengths. What inner working angle can they access? The dashed lines are the wavelengths of individual biosignatures. And then the shaded regions are the locations of the habitable zones for, up on top, a G star, a K star, and then an early, mid, and a late M dwarf. And so on the left, we have at a distance of 5 parsecs, and on the right, we have at a distance of 10 parsecs. So if any of these habitable zones are above the lines of the telescope, that means that that biosignature is potentially accessible to these coronagraph systems. So the ELTs should be able to reach biosignatures for G, K, and early and mid-M systems at, so they should be able to reach optical wavelengths, so the oxygen band, at 5 parsecs and even 10 parsecs for the most part. If you're looking at JWST or HWO, you can only really access C and K stars at you might be able to observe some M stars at optical wavelengths close by, but not further away. So feel free to take a look in more detail at this plot in my paper, but you can basically look at M dwarfs from the ground with ELTs, reflected light. There have been some case studies for using existing telescopes. So in this case, the VLT 8.2 meter telescope, using the sphere chronograph with coupled to the espresso high resolution spectrograph. And they basically looked at Proxima Centauri b and concluded that they could, in about 60 nights, which is about 3 years of observing time, they could observe Earth-like levels of oxygen on Proxima Centauri b with the VLT with a few upgrades to current instrumentation. And I think they are actually working on building a separate system to try to do this right now. But we'll see if that's possible. That would be great if we could do it with current telescopes. But what about the ELTs? We again do the same sort of Bioverse simulation, injecting pretty much the same inputs, but this time looking at reflected light and assuming some specific instrument performance models. And what we get is that we can, with the GMT in a nominal survey duration of 10 years, observe up to about 7 planets and look for Earth-like levels of oxygen. With the ELT, with its much larger collecting area, we could observe up to about 20 planets for oxygen. This already bodes way better than the transmission spectroscopy. We could now observe several handfuls of planets and look for oxygen around them. This is specifically looking at rocky planets, and so we did just sort of a nominal cutoff of 1.4 Earth radii for this simulation. But what if we go all the way up to the planet radius valley, so include all Earth/super-Earth planets? We can definitely observe a lot more. So with the GMT, we can observe on the order of 10 planets in a 10-year survey, or up to 10 planets, and then up to about 30 planets with the ELT if you include all super-Earths. And so that bodes very well, I think. But again, let's look at some real planet systems. We have a handful of nearby. These are all within 10 parsecs. Super-Earths, so we don't necessarily have a true Earth analog, or at least not that we know. All of these planets were detected through radial velocity measurements, so we only have a minimum mass. None of these planets are transiting, so we don't truly know if these are Earth-like planets. But with the ELT, we could probe for Earth-like levels of oxygen within about a week of observing time. With the GMT, it'll take on the order of a month or two, but still, that's a lot quicker than decades with transmission spectra. So these are our current best targets. Hopefully, in the next few years, large radial velocity surveys will identify even more and hopefully more promising candidates, but a lot of the focus is on Proxima Centauri b. Not only is it our closest exoplanet, but also it is the lowest minimum mass, and so we're hoping it is somewhat Earth-like and hoping it even has an atmosphere. And so far I've talked about just the first two modules of Bioverse, generating sample, simulating a survey. Haven't quite talked about testing hypotheses. So now that we actually have a planet population that we can look for oxygen, we can start to test hypotheses. So let's start with a simple hypothesis of, let's say we want to test the hypothesis that habitable zone planets, rocky habitable zone planets, all have oxygen. What kind of survey are we going to need, and what kind of parameters are going to be necessary to test this hypothesis? Well, if we have low values of eta Earth, so 5%, we need at least half of the planets to have Earth-like levels of oxygen. If your eta Earth value is something closer to like 30%, then only about a quarter of the planets need to have oxygen to test this oxygen habitable zone hypothesis. So we're just starting with some of these basic hypothesis testing, but we really do need some sort of large sample of planets to be able to test this. So hopefully in the next several years, right before the ELTs come online, we will have a larger population of at least super-Earths that we can go look for these biosignatures. And so in conclusion, I'm optimistic that JWST will detect atmospheres and will be able to disentangle that from the stellar signal, but we do need to make some progress. There's actually a paper that just came out today saying that there's a potential secondary atmosphere detection on an exoplanet, and that's slightly more favored than the stellar activity. So we'll see if that holds up with more data. But the ELTs really are the first telescopes that are poised to actually find biosignatures, or at least look for biosignatures. Transmission spectroscopy is going to be difficult for at least oxygen. We'll look into seeing if like methane or carbon dioxide are a little bit more promising from the transmission spectroscopy standpoint, but it looks like reflected light spectroscopy is really the way to go in the future. Really developing these instruments and really reaching with a combination of coronagraphs and high-resolution spectra the contrast we need to detect these biosignatures. And then the Bioverse framework is open source, very modular, and can be used to assess other molecules, other methods of observing, and test different hypotheses for ground and space-based telescopes. With that, I'll take any questions. Thank you.
Awesome talk, Kevin. So yeah, we have time for questions. So if anyone in the room wants to ask Kevin anything, or anyone online, feel free to raise your hand or post it in chat.
Kevin, can we go back a couple of slides to the plot where you showed the statistical power? Oh, wow, it was literally the slide before. Yes, that one.
Yeah.
I'm very curious what is going on at 0.6 to cause that purple bump.
That I would assume is just noise in the simulations. We do want to run this for longer. We do have a couple of bugs to work out to expedite the calculations. This took a week to run on a fairly low resolution grid on a supercomputer. So that I would just attribute to just, I wouldn't look too much into that.
Okay, cool. Thank you.
Yep, thanks.
Great talk, Kevin. Can you go back to your plot on the, yes, even before, the one slide before, yeah. There are huge uncertainties in both the curves. So, for example, if I want to observe something, the survey duration could be anywhere from 3 years to 17 or 20 years.
Mm-hmm.
What's driving those uncertainties?
Those uncertainties are largely driven by our uncertainties in orbital parameters. We're currently just assuming sort of uniform priors on these parameters, and it can be wildly different. So if we have better constraints on, say, like the inclination angle of the planet, we can better constrain sort of the phase information and how much light we're going to get from the planet at the time of observation. So yeah, they're wildly large uncertainties, but from a simulation standpoint, we don't necessarily want to make more constraining. We don't want to limit ourselves in these simulations, but you can see sort of the trend of how many years roughly. So you see how many planets and how many years it's going to take. But yeah, if we had true orbital parameters, like even with our known planet systems, we again don't know the inclination angle, we don't specifically know the albedo. And so if it's a very high albedo planet, it's going to take a lot quicker than something at very low albedo. So yeah, that's why the uncertainties here range from a couple days to a month. So yeah.
So we have more planets on this list that we can talk about.
Yeah,
There
yeah.
are more RV planets.
Yeah, these were the currently accessible the planets, and then the only ones that we could actually observe within 10 years that were currently known. So we can chat more.
We can, yeah, let's talk.
Yeah.
Great. Does anyone else have any questions for Kevin? I have one. If you want to go back to the the optimistic transmission case, just not really a question, but more just a conversation on, from the work that you've done, where do you see transmission fitting in to support these direct imaging? Because it's a pretty grim picture right here.
For biosignature detections, possibly. This is also specifically for oxygen. So again, there might be room for it for methane and carbon dioxide. So I'm not ruling that out because it looks much more promising for those, but I need to run these full Bioverse simulations rather than just saying it'll take O10 transit. How does that translate to a real survey? But for other types of planets, like other super Earths detecting other signatures in atmospheres of exoplanets, there is still a lot of room for transmission spectrum, just not necessarily biosignatures.
Looks like we have something in chat. So somebody, let's see here. they said that they disagree with your assessment of the role of spectral resolution. We do not need high spectral, you said that we do not need high spectral resolution in space because we do not have caloric contamination. For transmission spectroscopy, one needs enough resolution to tell apart the planetary features from other lines, and also at higher resolutions.
So for certain bands, yes, that's true. I guess I'm focusing on the oxygen band, which I don't think there's much contamination from other features around, say, the oxygen A band. So yeah, depending on what lines you're looking at, yeah, you might need to go to a different resolution.
Yeah, Nikolai, do you want to come off mute and say anything to that?
Yeah, I think the whole point of the instrumentation on the ELT is that they are supposed to be super duper stable in terms of wavelengths. And so we are looking at the features which will be moving. And so we need enough resolution to see the motion throughout the transit, if we're talking about transiting spectroscopy.
Yeah.
I also have a couple of other comments. I'm sorry, but I disagree with your optimism about reflected light. You know, there are different things that can make reflected or planets seen in reflected light to look very different in different phases. It could be weather, it could be clouds, it could be all sorts of things. And so getting reliable, reproducible information with reflected spectroscopy would require an atmospheric model. And that is very tricky because we are trying to recover atmospheric model and we need atmospheric model to analyze the data. And so that's kind of, yeah, biting your own tail.
Yeah, yeah. So these, I will add the caveat that these are fairly optimistic upper limits of what we could potentially detect. Because again, we're assuming a more Earth-like planet, but most of these are going to be around M dwarfs, and so we need better models of M dwarfs, and specifically, we really don't know about the albedo and changing cloud effect and how that's going to affect our observations. So we're doing the best we can with just our input simulations and sort of randomizing things, is again why we have these really large uncertainties in our measurement.
Yeah, but otherwise very useful and interesting work you're doing. Thank you.
Thanks.
Great, thank you. Does anyone else have any other questions for Kevin?
Yeah, I really like the plot where you show the different ELTs and the habitable zones on it. Yeah, I think it's fascinating to see M0 versus M8.
Yeah.
So we often talk about M stars, but I think we really need to start talking about early M stars versus late M stars, because obviously massive range. My other question is in relation to this about the transition from the visible into the near infrared. I know you focus completely on O2 for the reasons you talked about, but it looks like some of these ELTs will really be able to stretch into the near infrared, especially for the nearest planets. Do you feel that the scenario is as optimistic for those yourself as it is for O2?
I think so, as long as we can observe it. I think I haven't looked directly into the specific lines for CO2 and CH4. Oxygen is it's constrained to a fairly narrow wavelength space, whereas these other lines are fairly broad, and that could complicate, for at least the reflected light scenario, how do we collect those photons and how do we disentangle the signal. I think some lines of methane and CO2 are sort of overlapping too, and so disentangling that is going to be a little bit more challenging. So that's why oxygen being kind of isolated in its own little band was very nice and being fairly narrow. But when we go to other molecules, we definitely want to do those in the near future.
I just want to point out my favorite stars, K stars, are all half zones, and they're oxygen, many other features that we could do with K-dwarf stars. Please focus. Don't ignore our.
Yes, yeah, absolutely.
Don't ignore our middle sisters.
Yeah, we aren't, so our simulations actually include all stars. It just happens that, that M dwarfs are mostly for contrast reasons, the only real accessible ones. From the ground, yes.
Great. All right, any other questions? Well, let's thank Kevin again for a great talk. And I believe Kevin has some time this afternoon if anyone wants to meet, so please come up and talk to him about that. So thanks everyone for coming, and thanks everyone online for joining.